We feel gravity every day. It keeps us grounded. It makes objects fall. From the moment we wake up and place our feet on the floor to the times we drop something accidentally, gravity is always at work. It's a constant, invisible force that shapes our daily lives. But have you ever stopped to think about how weak gravity actually is? Despite its omnipresence, gravity is surprisingly feeble compared to other forces in nature. Consider this. You can easily lift a book with your hand. This simple action, which we take for granted, is actually quite remarkable. By doing so, you are overcoming the gravitational pull of the entire Earth on that book. The Earth, with its massive size and weight, exerts a gravitational force on everything, yet your muscles can counteract it with ease. This simple act reveals a profound truth. Gravity is incredibly weak. Think about magnets. Even a small magnet can demonstrate this weakness. A small magnet can hold a paperclip against the pull of Earth's gravity. This tiny magnet, with its modest force, can easily counteract the gravitational pull that the entire planet exerts on the paperclip. This illustrates the stark difference in strength between gravity and electromagnetism, another fundamental force. Electromagnetism is immensely stronger, governing the interactions between charged particles. Gravity's weakness is a puzzle, especially when we consider its profound influence on the universe's grand structure. Despite its feebleness, gravity is the architect of galaxies, stars, and planets. Why is gravity so much weaker than the other forces? This question has intrigued scientists for generations. This question has puzzled physicists for centuries. Great minds like Newton and Einstein have grappled with the mysteries of gravity. It hints at a deeper, more fundamental theory of gravity waiting to be discovered. Perhaps our current understanding is just the tip of the iceberg. Could there be hidden dimensions where gravity is strong, but its influence is diluted in our observable universe? These hidden dimensions might hold the key to unlocking the true nature of gravity. The search for answers takes us on a fascinating journey into the heart of modern physics. As we explore the cosmos and delve into the fabric of reality, we inch closer to understanding the subtle yet profound force that is gravity. To understand gravity's peculiarity, we must introduce the four fundamental forces governing the universe. These forces dictate how particles interact and influence each other. They are the strong force, the weak force, the electromagnetic force, and of course, gravity. The strong force is, well, the strongest. It binds atomic nuclei together, overcoming the immense electromagnetic repulsion between protons. The weak force is responsible for radioactive decay. Electromagnetism governs everything from light and electricity to the chemical bonds holding molecules together. Then there's gravity. The weakest of the four, it governs the large-scale structure of the universe. It holds planets in orbit around stars and stars together in galaxies. Despite its weakness on atomic scales, gravity's influence is felt across the vast cosmic expanse. Gravity's weakness is counterbalanced by its incredible reach. Unlike the other forces, gravity's influence extends infinitely, albeit weakening with distance. This far-reaching effect allows gravity to shape the cosmos. The moon, despite being much smaller than the sun, still exerts a gravitational pull on Earth, causing tides. Galaxies, vast collections of stars, are held together by their collective gravity. The elegant dance of celestial objects is a testament to gravity's pervasive influence. Gravity's reach is a consequence of its universality. Every particle with mass or energy contributes to the gravitational field. This cumulative effect becomes significant over astronomical distances, shaping the universe we observe. Our understanding of gravity has evolved significantly over time. Isaac Newton described gravity as a force acting instantaneously across space. His law of universal gravitation elegantly explained the motion of planets and falling objects. However, Newton's theory had limitations. It couldn't explain certain subtle effects like the precession of Mercury's orbit. Enter Albert Einstein and his revolutionary theory of general relativity. Einstein reimagined gravity not as a force but as a curvature in the fabric of space-time caused by mass and energy. Imagine a bowling ball placed on a trampoline. The ball creates a dip, distorting the trampoline's surface. Similarly, massive objects warp space-time around them. Einstein's theory provided a more complete description of gravity, explaining the anomalies that Newton's theory couldn't. It also predicted new phenomena like gravitational lensing, where light bends around massive objects, confirming the warping of space-time. Section 5. The enigma of extra dimensions. Could gravity be hiding? Despite its successes, general relativity doesn't tell us why gravity is so weak compared to the other forces. The electromagnetic force, for instance, is vastly stronger, governing the interactions of charged particles with ease. This is where the intriguing concept of extra dimensions comes into play. These dimensions, if they exist, could provide the missing pieces to the puzzle of gravity's weakness. String theory, a leading candidate for a unified theory of physics, suggests that our universe might have more than the three spatial dimensions we perceive. Imagine a tightrope walker, balancing carefully on a rope. From a distance, they appear confined to a one-dimensional line, moving forward and backward. However, an ant crawling on the rope experiences an additional dimension, the circumference of the rope. This tiny creature can move around the rope, exploring a dimension invisible to the tightrope walker. Similarly, extra dimensions could exist curled up at incredibly small scales, invisible to our current experiments. These dimensions might be compactified, hidden from our everyday experiences. Could gravity be leaking into these extra dimensions, diluting its strength in our observable universe? This leakage could explain why gravity appears so weak compared to other forces. This is a fascinating possibility that physicists are actively exploring. Researchers are devising experiments and theories to detect these hidden dimensions and understand their impact on gravity. If true, it could revolutionize our understanding of gravity and its place in the cosmos. The discovery of extra dimensions would not only solve the mystery of gravity's weakness, but also open new frontiers in physics, transforming our comprehension of the universe. Section 6. Dark matter, the invisible hand, strengthening gravity's grip. The study of gravity is further complicated by the mystery of dark matter. This elusive substance, which does not emit, absorb, or reflect light, remains one of the most enigmatic components of our universe. Observations of galaxy rotation revealed a significant discrepancy. Galaxies were spinning much faster than they should, given the visible matter they contained. This unexpected behavior puzzled scientists for decades. The gravitational pull of the visible matter wasn't enough to hold these galaxies together. Without an additional source of gravity, these galaxies would have flown apart. This discrepancy led scientists to propose the existence of dark matter, an invisible form of matter that doesn't interact with light, but exerts a gravitational pull. This dark matter forms a halo around galaxies, providing the necessary gravitational force. Dark matter is thought to make up a significant portion of the universe's mass, providing the extra gravity needed to hold galaxies and galaxy clusters together. Without it, the large-scale structure of the universe would be vastly different. While we haven't directly observed dark matter yet, its gravitational effects are undeniable. One of the most compelling pieces of evidence comes from gravitational lensing, where light from distant objects is bent by the gravity of dark matter. Its existence further highlights the complex interplay between gravity and the universe's hidden components. Understanding this relationship is crucial for a complete picture of cosmic evolution. Unraveling the nature of dark matter could hold crucial clues to understanding gravity's true nature. As we continue to explore the cosmos, the invisible hand of dark matter remains a key piece of the puzzle, guiding our quest for knowledge. Section 7. The quantum world, where gravity's influence fades. On the opposite end of the scale, in the realm of atoms and subatomic particles, gravity's weakness becomes even more apparent. In the quantum world, governed by the bizarre laws of quantum mechanics, gravity's influence is negligible compared to the other forces. Quantum mechanics describes particles as existing in a superposition of states, constantly fluctuating and interacting. At these minute scales, the gravitational attraction between particles is so weak that it's completely overshadowed by the other forces. This disconnect between gravity and the quantum world is one of the biggest challenges in modern physics. We lack a consistent theory that can describe gravity's behavior at both the cosmic and quantum levels. Finding such a theory of quantum gravity, is a holy grail for physicists. Section 8. The future of gravity. Unveiling the universe's deepest secrets. The quest to understand gravity continues to drive scientific exploration. From searching for ripples in space-time called gravitational waves, to studying the extreme environments around black holes, physicists are pushing the boundaries of knowledge. New telescopes and experiments are being built to probe the universe's deepest secrets. These endeavors promise to shed light on the mysteries of dark matter, dark energy, and the fundamental nature of gravity itself. The weakness of gravity, once a puzzle, is now a gateway to new discoveries. By studying its subtle effects and seeking a unified theory, we are embarking on a journey to unravel the universe's most profound mysteries. The future of gravity research is bright, filled with the promise of groundbreaking discoveries that could revolutionize our understanding of the cosmos and our place within it.